Hello, everyone. It's a great honor to share my research about end-to-end robustness for sensor reasoning pipeline in adversarial environments here with you. My name is Bo Li, and I'm system professor from UIUC. As we all know that machine learning nowadays has been ubiquitous in the world. It has been applied to different domains to help make our life better. For instance, autonomous driving, intelligent medical treatment, and smart city have been built up to improve the quality of our life. And AlphaGo has shown that the AI has certain power which can perform better than human on certain tasks. However, even such very powerful machine learning techniques have also brought a lot of security and privacy concerns for us. For instance, in 2016, the White House associate Twitter account was hacked via phishing emails, which spread the rumor that the White House has been attacked. And it triggers the autonomous trading bot to dump a large amount of stocks within seconds and swipe about $136 billion within seconds. And that's something happened in real world. And also in Australia airport, the biometric recognition system has been deployed for safety screening, which has raised a lot of privacy concerns. So with these concerns, we can also look at some real-world examples and think about what even if we are facing such vulnerabilities of the machine learning models, what we can do to improve the robustness and towards the trustworthy machine learning or AI. So here is our previous result showing that given the real-world stop signs, which may contain some graffitis or certain patterns on the sign itself, we actually show it's easy for a human to generate certain adversarial so-called stickers that can be stick onto the stop sign itself in real world. And you can see here each column is a different types of adversarial perturbation in real world, and each row shows different angles and distances. And this shows that with certain adversarial behaviors, it's possible that all the stop signs in these slides are misrecognized as speed limit sign 45, which can raise real consequence if a car will not stop when they see such adversarial physical stop sign. And here is a quick example that dynamic experiment that when there is a car driving by, on the left-hand side is a perturbed stop sign, and on the right-hand side is a control experiment, which is a vanilla stop sign. And if we look at the captions, we can see with different speed and the distances of the car, the left-hand one is always misrecognized as a stop sign. So this actually raises us a lot of thinking about, okay, we know in real world, we can exactly see that the machine learning systems, either autonomous driving or medical treatment, which are mission critical here, can be manipulated in certain way by adversaries, so that cause severe consequence. So in this talk, I will mainly talk from three perspectives to look at how and what strategies we can use to improve the robustness of machine learning models, so that we can certify the end-to-end robustness, or we can verify the sensitivity or the stability of the machine learning models, such that we can end up with a more trustworthy machine learning or AI systems. And the first, we'll talk about the certifiable robust sensor reasoning pipeline, and then we'll talk about how to leverage game theoretical analysis to analyze the robustness or vulnerability of machine learning models, and then I will talk about the other intrinsic information that can be leveraged in either the data or machine learning model itself, such that we can improve the robustness of machine learning models. So first, let's look at this end-to-end robust sensor reasoning pipeline and see what guarantee we can obtain here. And here is a higher level overview of this framework. So we know that as machine learning has been applied to many mission critical scenarios, certifying the machine learning model robustness has become increasingly important. And many previous work, however, only focus on the robustness of independent machine learning or even just ensemble models, and only certifying a small magnitude of the perturbation from the adversarial perspective. So here in this sensor reasoning pipeline, the goal is to promote the generic sensor reasoning pipeline here, which can contain both sensing components, which you can see on the left-hand side is a bunch of you can view it as a bunch of neural network models, or it can be other machine learning models, logistic regression, decision tree, whatever machine learning model or statistical machine learning model it is. And then we compose it with a reasoning component, which can be realized as Markov logic networks or Bayesian networks, which is graphical models can incorporate domain knowledge. And then we can enrich the domain knowledge with these graphical models. And the question we want to ask here is, can the domain knowledge help improve the learning robustness, and how much we can formally certify this end-to-end robustness for this sensor reasoning pipeline? So this is a question we want to ask. And here we can see there are additional challenges and opportunities within this pipeline. So concretely on the sensing component phase, we actually have the neural net. For example, we take the example of neural networks, and who can output their prediction as a set of Boolean variables. And this set of Boolean variable can be viewed as a prediction for certain classes. And those Boolean variable can be sent to the reasoning component, which will use this set of Boolean random variable in the statistical reasoning models, and then to produce the final output, which is also a set of Boolean variables. And this pipeline can actually be applied to a wide application such as reinforcement learning and information extraction, which I will show some experimental results later. But let's focus on the theoretical analysis first. So we can see that given such a pipeline, our goal is to certify that during the inference, given a perturbation at the input, which is the eta here, like take the image as an example, we have certain magnitude of perturbation added to the image, just as adversarial examples. And then after passing this reasoning pipeline, we have some uncertainty at the output of the reasoning component, which is a CS here. And this uncertainty will again be passed to the reasoning component, and then we will eventually get the final uncertainty, which is a CE here. Our goal here is to bound the CE given the knowledge of eta here, so that we can bound the end-to-end robustness. And we will give the formal definition in the next slides. So here I mainly want to emphasize that there are both challenges and opportunities for this pipeline. For example, in terms of the challenge, we can see that different from the neural networks whose inference can be executed in polynomial time, but the many reasoning models such as Markov logic networks, which we know can be Sharpe complete for during the inference. So this raise the hardness for the computation. However, this also gives us the opportunity because as many reasoning models define a probabilistic distribution in the exponential family, so we have more function structures than in neural networks that we can leverage and potentially make coming up with robust guarantees, which essentially make the solution for a min-max optimization problem on top of the graphical model reasonable. So here, in this sensing reasoning component pipeline, we'll mainly talk about two questions. One is checking the provable robustness in the reasoning component feasible when the inference of the reasoning component is Sharpe complete, right? And we will show it is possible and we can compute it efficiently. And second, we'll show when we can efficiently compute it, how we can guarantee the end-to-end robustness given some oracle towards the statistical reasoning, meaning we know what's the knowledge we want to incorporate in the reasoning component. Okay, so next, let's look at a concrete example of how we can incorporate certain knowledge into the this sensing reasoning pipeline. So we can see more concretely here we have a set of sensing sensors, and we call SI. And then we have a reasoning component, which is R. And for each sensors, they will output a probability for certain classes, which we call it PIX, given the input data X. And the output of a reasoning component is the new Boolean variable based on the output of the sensing model, which is the R over the PX, and take the expectation over it. So we can see that one example of such knowledge is for ImageNet classification. So we know there is a hierarchical knowledge for ImageNet dataset, and here the sensing model corresponding to the classifier for each specific class in the ImageNet. For example, here it's a sensing dog or the sensing animal here, and the reasoning component here output a Boolean variable for each specific class, and the reasoning component then endorses the domain knowledge, such as if an image is classified as a dog, then it must be classified as an animal, such hierarchy knowledge. So we can see here in each sensing, they output the dog or cat or animal, and then for this output of the sensing models, there is a factor graph which can incorporate the factor among these sensors, so that we can learn the weights later for each factor within the graph, and emphasize different types of knowledge. And next, let's have the formal definition of our end-to-end robustness for this sensing reasoning pipeline. So basically, we can see if given the CI/CE, which is the input, the magnitude of perturbation bounded for the input data and the output of this end-to-end pipeline, and we hope we can bound the output of the reasoning component given the input and the perturbation of the input. So we know no matter as long as the input of the perturbation is within certain range, for example, CI here, and we know the end-to-end output for this pipeline will be bounded by CE. So that's our goal. And here are some specific variables we will use later on in our analysis. So basically, we know there are within the reasoning component, there are some interface variables which connect with the sensing models, and there are some interior variables within the reasoning component or the graphical model component, and we have different factors for these two types of variables as well. And we can see on the higher level, the output of the MLN reasoning component is that it's a probability of Z1 divided by Z2. So here Z1 defines the possible word that makes the knowledge true, and the Z2 defines all the possible words that can happen in this graphical model assignment. So basically, from this high level intuition, you can see the hardness of calculating how many assignments are possible here within this graphical model becomes the main bottleneck for our computation. So here we will first look at the hardness of this problem of the for certifying the end-to-end robustness for this sensing reasoning pipeline, and we can see that given this Markov logical model as an example, we can show the above the graphical model itself can define a joint probability distribution among all the variables, and for each possible word, they design a set of assignment for the possible word. And here we have the definition for counting problem, which exactly counts the assignment for a set of first order logic rules. And we can see when we write it in this way, it looks very close with the formulation as the robustness that we want to certify here, which is we just rewrite the robustness as the second definition. And here we can see we can reduce the robustness of sensing reasoning model to the counting problem, which shows that the end-to-end robustness certification for the sensing reasoning pipeline is Sharpie complete. However, a good news is that it's still possible to give the provable robustness for the end-to-end reasoning component here, even though the inference time, the factor graph inference is Sharpie complete, but given certain knowledge, for example, there are multiple ways to accomplish this. For example, when the factor graph is of a small tree-wise, or one can apply exact inference algorithm for it, or one can also construct the Markov logic net program such that exact statistical inference is possible. Or there also exists a range of approximation inference algorithm for ML and inference. So here we can show that as long as we have access to an exact oracle for the statistical inference, then provide a novel algorithm for the upper and lower bound of this sensor reasoning pipeline is possible. So here is how we can do it with this lemma. So basically we can see with the magnitude of perturbation as C, we can exactly solve the max problem here given the min-max structure. So basically we know even in the traditional neural networks, when we want to certify the robustness of it, we are trying to essentially solve a min-max problem. And because of the non-convexity and non-monotonicity of the neural networks, solving exact min-max problem for it is hard. But here, because we have some knowledge about the possible world due to the domain knowledge we can get, it is possible for us to solve the min-max problem here. So we can see here, remember that the D1 defines the possible words that give you the ground truth assignment aligned with the knowledge, and Z2 defines all the set of possible words. And we can see the conclusion is that when we have a ratio lambda larger than 0 or the smaller than -1, we can exactly get the solution for this min-max problem. And if the lambda is within -1 to 1, we have to sample with MCMC and then bound it to analyze the magnitude here, the epsilon here. So that is to say, with exact knowledge about what can be true in this sensing reasoning pipeline, it is possible to certify the end-to-end robustness. So on the high level, I want to give some intuition about why it is possible. So the fundamental reason lies in the structure of the reasoning component. We can see here with a range of properties. For example, all variables are factors are only output non-negative values. Unlike in neural network, it could range from negative to positive. This makes it possible, and also the distribution is in the exponential family with a limited weight sharing, and the reasoning component also enjoys some monotonicity properties. For example, with this like 1 lambda larger than 0, it monotonically increases. So in this way, because of the non-negative and the monotonicity properties, the min-max optimization problem becomes solvable here in the MLN program compared with traditional neural networks. And moreover, these properties hold for general morphologic networks, which is good, and make us believe that this sensor reasoning pipeline provides a unique opportunity for us to further improve the robustness of ML applications by integrating different domain knowledge, especially given that the robustness of a single machine learning model or ensemble can be harder to certify in real world. So here, I think this sensor reasoning end-to-end pipeline actually give a more promising way for us to certify the end-to-end robustness in real world for machine learning models by incorporating human knowledge to it. And here I want to, after the theoretical analysis, we show that even though it is hard, by accessing some knowledge, for example, the domain knowledge and giving the constraints for approximating the MLN inference time, we can get the end-to-end robustness for different sensing reasoning pipelines. Here, empirically, will show how tight it is. Of course, theoretically, we can show it is tight for MLN program at least, and it is also possible for some structures for Bayesian networks. And empirically, we want to show whether it can improve in practice for state-of-art applications. For example, here there are two applications. One is state-of-art OCR digit recognition model, and second is NLP stock data sets for information extraction. And here we can see different tables shows the with and without knowledge, and we calculate the end-to-end accuracy empirically or the certified accuracy. And here we can see if shown shows the magnitude of the input perturbation. And we see that with a larger magnitude of such perturbation, with knowledge, like this sensor reasoning pipeline can certify much higher both vanilla benign accuracy and the certified robustness accuracy than the machine learning model without any knowledge. So this is showing that with human knowledge, it is possible to not only improve the benign accuracy of the sensor reasoning machine learning model pipeline, but also the certified robustness accuracy. And similar for other scenarios as well. And besides showing the benign accuracy and the certified robustness accuracy improvement, we also want to show how tight the robustness certification could be when we incorporate some domain knowledge. For example, again, this is 2 examples on OCR and NLP applications, and this the magnitude of the bar or the height of the bar shows the certified margin, which is the lower bound of the correct class minus the upper bound of the wrong class. So basically, the higher means the more confident it is. And here we see, for example, from the OCR experiment, on the left-hand side, the green background shows the correct, and on the pink one shows incorrect, and the blue one shows with knowledge, and the red one shows without knowledge, which is only a single neural network. And we see that with knowledge, when the perturbation magnitude is small, almost all the blue bars are in the green range, meaning that the blue bar are very confident to correct the prediction to the right range with high confidence. But more interesting, we find that sometimes when the magnitude of perturbation is very large, it is possible that we can see some blue bars are in the pink range, meaning that with knowledge, I'm actually more confident to drag the prediction to be the wrong class, meaning even I'm wrong, but I'm quite confident because I have the knowledge. So this is very interesting, but unfortunately, we hope will not happen in practice. So one solution to this is we still need to improve the robustness of the knowledge itself. So here, for example, we are using the knowledge as the hierarchy, right? Like if you are a dog, you should be the animal. However, this knowledge is actually not that robust because the assignment for certain first order logic rules are not unique. So it means you can have different assignment and some assignment could be wrong. So this way, the knowledge itself is not robust. So next, interesting direction, I think, for this end-to-end sensor reasoning pipeline is that we need to find the robust knowledge in terms of the uniqueness of the assignment for certain first-order logic rules. And then that will, for sure, confidently correct the prediction of any perturbed input for machine learning models. So this is the interesting future direction. And the quick takeaway from this robust end-to-end sensor reasoning pipeline work is that we show that it is possible to certify the end-to-end robustness of a sensor reasoning machine learning pipeline, although the robustness of the reasoning component is sharply complete in general, and giving oracle to the statistical inference, meaning we know the oracle how to calculate the possible word given the domain knowledge, and it is possible for us to efficiently calculate the certified robustness bound. And in practice, we know knowledge can indeed improve the certified end-to-end robustness for machine learning model pipeline, which can actually help to certify a larger magnitude of perturbation compared with current certified robustness for single neural networks. However, the important next step for us is to understand and efficiently collect robust knowledge to improve the certified end-to-end robustness.